falls over the audience, that's a sign that something is about to happen. So, good afternoon, ladies and gentlemen. This is another in a series of seminars that we hold in the I for Energy Center. Welcome on behalf of my colleague, Gaiman Yi, who is generous enough to help support the lunch for these meetings. Welcome to our viewers on the web, especially our sister CITRIS campuses at UC Santa Cruz, Davis, and Merced. Before I introduce today's speaker, the program for this semester's series of seminars shows this as being the last one, and that is no longer true. We will have one next Friday at noon, April 30th, not in this room, but downstairs in room 250, and the speaker will be Christine Ho. She will be talking about some fascinating battery technology that is quite applicable for a wide variety of things, among them being solar energy storage. Today we are very pleased to have Professor Dan Farber, who is a professor of law at the law school here at Berkeley and is the chair of the Energy and Resources Group, or ERG, also here at Berkeley. He is the faculty advisor, the faculty director of the Center for Law, Energy, and the Environment. Dan went to the University of Illinois for all three of his degrees, the BA, the MA, and the Doctor of Jurisprudence. He was a law clerk for Justice John Paul Stevens at the Supreme Court of the United States. Practiced law in conventional law practice, where he focused primarily on energy issues, and that's the linkage to the theme that we've been talking about here in these I for E seminars for the last several years. He is a widely published author and is an expert on the use and the abuse of information in environmental law. So without further ado, let us welcome Professor Dan Farber this afternoon. Dan, good to see you. Now turn that on if you haven't done so already. It's this button, hold it in, and you're on.
Well, thanks. It's great to be here today. I'm talking, as you can see, about climate models and how they are used or sometimes perhaps abused in the process of making policy and in the legal process. Climate models are fundamental to our understanding of climate change, although they're not by any means the only reason for believing that we're in the midst of serious climate change. And they are also central to thinking about policy. So I think it's important for all of us from outside the world of climate scientists to try to get a handle on these models, understand at least a little bit about how they work, and then think about what they tell us and what their limitations are. So this is a picture of the climate system. As you can see, there are a lot of pieces. There are a lot of moving parts here. And of course, this little picture is replicated for every portion of the globe, with some modifications for the water. We don't have, in some sense, a deep understanding of the dynamics of global climate. I mean, in the sense that we have some kind of statistical model, for example, of the overall evolution of the climate system. The system is too complex and has too many kinds of interactions between very different components. And as a result, when we think about climate, what we need to do is to look at all of these different components and at their interactions and try to model all the different pieces of this. So you can see that this is going to be no small undertaking. It includes everything from what people are doing on land to wind stress on the ocean, what exactly happens when the air starts moving water around in the form of waves. It includes the hydrological cycle, changes in solar inputs, etc. So very complex. And so here's the basic idea behind modeling it. I should stress that I'm not a climate scientist, or let alone a modeler. But I think it behooves all of us to at least understand the basics. So you can see that this globe is divided into a grid, and that on top of that grid, for each sort of grid square, there are cubes layered upward. And in the ocean setting, the cubes are also layered downward into the ocean. So the very earliest models were very crude. They, for example, didn't include ocean currents. They had only very large cubes and not much detail about those. And so these are all the different things that need to be brought into the model. What's going on in the ocean and the interactions between ocean and air, precipitation, clouds, what's going on the ground, solar radiation, how much of it's getting bounced back upward. What do you do with that? Well, what you do is you take every one of those little cubes and basically you model that cube. Right, so every one of those little cubes, you look at the equations that govern, for example, the transfer of heat inside and outside. You figure if there's air moving in that cube, it's going to move into the next cube, and vice versa. You look at what kinds of clouds are in the cube at any given time and how much sunlight they're reflecting upwards. You look at rain and how much heat is being transferred through precipitation. So what you do is you have like all these cubes, and every time you compress the cube by half, you're drastically increasing the total number. You take every one of them, you figure out from one really half hour to the next what's going on in each cube. And the only reason we can even contemplate doing that is because of the tremendous increases in computing power that we've seen over the last few decades. These models are really big, and they can take days or weeks to run on a supercomputer. But the idea is very simple. Just look at each different cube, look at its neighbors, keep tracking it every half hour for, say, 50 years or a century. Right? So in a way, it's kind of a brute force approach, right? We look at all the little pieces of this, we track all of them, and we just keep grinding and crunching away. Now, what have we learned from these models? Well, one thing that we've learned is that we can be pretty sure, given a certain amount of increase in greenhouse gases, say doubling greenhouse gases from the pre-industrial level, we can be sure that there will be at least a certain degree of climate change, somewhere in the neighborhood of 1 to 1.5 degrees Celsius in the long run. Right? The models almost never show anything less than that, and they never show cooling. Right? I should say that there are a couple things I should add. There's more than one model. There are something like 20 different climate models out there. And they don't always completely agree with each other, which is probably good because we kind of need to have a diverse set of parameter assumptions and inputs and modeling techniques in order to have some confidence in the results. So they don't always agree with each other, and if you do a bunch of runs on the same model, you're not always going to get out in the same place. You're not always going to have the same history because there are a lot of feedback effects, and so you can start with just a small change, and it builds into a larger change later on. So we don't have absolute certainty about any of these things, even within a given model, let alone across models. But we can be quite confident of the existence of climate change, its likelihood in the future, and that it will be at least at a certain level. As you can see here, however, we're a lot less sure about the high side of climate change. That is, although there's good agreement about the sort of lower end bound of the distribution, upper end is much less clear. Right, so this is, I think, one of the basic issues for climate policy right here is that we're faced with some uncertainty about how bad it's going to be, right? 1.5, 2 degrees is something we can probably, I think we can probably live with, although not without pain. You get up to 4 or 5 degrees, 6 degrees of change, and you're just in a different world. I think 6 degrees, for example, is the difference between today and the last ice age, right? So we're talking about really drastic changes, and we don't have a really clear understanding of where the upper end of that distribution is. Now, these models are better at doing some things than others. They're good at temperature. We can test them by doing things like starting them in 1900 and seeing how well they replicate the 20th century. So they're good at temperature. Precipitation is harder. And the reason, I think there are a couple of reasons why. Precipitation actually turns out to be really complicated. First of all, clouds are complicated. One of the things that we can't yet model from first principles, I shouldn't say we, but we in the sense of humanity. We can't model clouds from first principles. They're really complex, dynamic, turbulent systems. So the climate models have to basically use empirical approximations to cloud formation. So clouds are difficult. And then the trouble with precipitation is it's sort of a dichotomous event. If it rains, it rains. If it doesn't rain, it's not raining. So you've got this sort of threshold effect due to the question of when the water condenses, how much it condenses, how cool it is. So it's difficult. In addition, once it hits the ground, it evaporates again, forming new clouds. And to understand that, you really have to know a lot about soils and plants and all kinds of other things. And at that point, you're obviously getting really deep, literally in the weeds of doing the modeling. So precipitation is tougher. And getting down to a fine scale of granularity is difficult. And you can see why that would be, because those cubes, even today, are pretty big, right? So you're looking at a pretty granular map of the world. And as you get into the most fine-grained events, it's also going to be more sensitive to surrounding conditions. Whereas if you're averaging over a continent or half a continent or something like that, you can get a better job. If you're averaging over the whole globe, even better yet, because mistakes in one place are likely to cancel out mistakes in another. So we don't know as much about precipitation as we'd like, and we don't know as much about local events as we'd like. I'm not really planning to talk about this, but that latter problem, the regional problem, is particularly important if we're concerned about climate adaptation. Because we don't want to just know what's going to happen to rainfall in North America generally. We want to know what's going to happen in, say, Northern California. And even better yet, on the Russian River. So this is an effort to kind of pin down what we know and what we don't know a little bit better. Climate sensitivity. It took me a long time. It took me a while digging into this stuff to actually get a definition. Climate sensitivity represents the temperature change in equilibrium, which is down the road quite a ways, from doubling the pre-industrial CO2 level. Right? So it's not what's going to happen to the climate tomorrow. It takes the system a long time to get to equilibrium, so this could be, a few centuries out in the future before you actually hit this number. But it tells you something about how sensitive the system is to changes in radiative forcing and to the amount of heat that's retained. The first order effect's pretty easy. I mean, it's pretty easy. We know about carbon dioxide, we know about molecular bonds and radiation and all that. So we can have a pretty good estimate of sort of the most immediate effect of climate change, but what makes it so hard are all the feedback effects. And that's why we can't be absolutely sure. But what we find is, looking at the various models, a 90% probability the climate sensitivity is between 2.4 degrees and 5.4 degrees. So that, in other words, we're in the range between bad and terrible in terms of climate sensitivity. There's very little chance that it's below 1%. The models allow sensitivities greater than 8%. although I gather that there are kind of empirical reasons based on the climate record for thinking that that's probably high. Now, there are some things to think about in terms of this quantification. These quantifications are based on the models. So here you can see a little bit about what the different curves look like, right? And the degree of these are different models, the averages of different models, et cetera. Now, one of the problems is that these are based on the models, but we don't have any. We can't be sure. Let me put it that way, that the models encompass all the probabilities, right? It's possible that the models all have defects in common. That, you know, we have less reason to think that as time goes on, but it's still always a possibility. And there's the question of how to weight the outputs from different models, which is sort of a technical issue, but at least has some effect on how you come out on these things. Now, this is showing you why those feedback effects are so important. And how they sort of push the curve out, because positive feedbacks seem to be more important than negative feedbacks, although there are some negative feedbacks. If you evaporate more water, on the one hand, water is a greenhouse gas. On the other hand, if you have more clouds, they reflect more sunlight during the day. But then on the third hand, at night, those same clouds reflect heat back to the ground, right? So very tricky feedback effects here, but quite critical. If the Earth were a featureless ball bearing floating in space with a uniform atmosphere that didn't have any current, especially didn't have any water, we would be in a much better position to predict the future. Right? Water is a big part of the problem. Living things are another big part of the problem. And then you add on relatively minor issues like terrain and how that could affect weather. So one of the reasons I personally spent a lot of time looking at this is I devote a lot of my time to climate change, and I thought, gosh, I'd feel kind of dumb if it turned out to be a mistake. And so I really wanted to take a hard look and make sure, not that I agreed with the scientific conclusions because I'm not a scientist, but that scientists were engaged in kind of a rigorous process, that they were critical of their own findings, that they were doing things right. And that's pretty much what I did find out. So that was reassuring. It was less reassuring to find out about some of the uncertainties, but those are just issues that any policymaker has to look at. Now, the next thing I did was look at the economic models of climate change, which are very important in policy circles. You find a lot of debate about the implications of these models. Many economists in the US especially think that the models indicate a go slow approach to dealing with climate change. That is, that we should get really serious about climate change, but not for 3-4 decades from now. And in the meantime, what we should have are modest controls that gradually escalate. So these same economists, for example, thought Kyoto was a bad idea, don't think we should have stringent caps on greenhouse gases, et cetera. And I had read quite a bit about these sort of models and the economics of climate change previously. It was kind of a shock, actually, when I looked at the climate models that the economists were doing, because they are like, I don't know, a couple of orders of magnitude less advanced than the physical models. Of course, they have to build on the physical models as well. But if you look at the model, I think one way of capturing this is that the leading sort of model that you see used by Nordhaus at Yale is built to run on a PC, as opposed to what the scientists are doing, which take weeks on a supercomputer. That gives you a sense of the difference in terms of the complexity and detail that's built into the models. And when you go and look at the models, what you keep finding when you read the articles is, well, we don't really have a good way of modeling this or that, but we took a stab at it. Or we asked some experts and averaged their opinions, or something like that. So when you read the fine print, there's a lot of uncertainty about these models that the economists acknowledge. But too often, especially when they're writing for a policy audience, the uncertainty disappears when they state their conclusions. So the same economist who's saying, we really don't understand technological change, so we just decided to assume, the same rate of growth forever in productivity as today because we have no clue about how that works. At the end, we'll say, Kyoto is an economic disaster, and, when really the best you could, what they ought to be saying is, given a very rough, imprecise stab, back of the envelope calculation, it looks like Kyoto may not be economically justified. So I don't object to the crudeness of the models because you do what you can, given the state of the art. Human beings are a lot more complicated than clouds, and we can't even do clouds very well. So I don't object to the crudity, but it does bother me that people are overselling their conclusions. And I certainly think that the results of those models should be taken with some care. The other thing that's kind of striking is that economists are not nearly as good as the climate people at trying to validate their models. Right? So the climate scientists will take the model, feed in 1900 parameters, let her run from there, compare that with 20th century weather history to see whether they're getting it, about right. And are they producing things like El Nino? Do they have the right kinds of temperature changes coming at the right times and so forth? And you never see that with economic models, right? You never see these people saying, okay, let's start the model of the economy in 1900 and see if we can, predict the Great Depression. Or even let's see if it gets current energy patterns right today. So that makes it much harder to know how seriously we should take predictions about the future. A lot of predictions have not turned out to be very good. People put a lot of money into modeling energy use because it's really economically important for the industry, for consumers, and other things. And over time, those predictions have not been super. They've tended to be off partly because they don't anticipate policy changes that impact energy use. One of the problems in the economic models is we don't really know how much it will cost to reduce greenhouse gases, especially as you go past the next couple of decades. We get some ranges. I think they're informative. Why don't we really know? Well, part of the problem is it depends on technology that doesn't exist yet, right? And because it doesn't exist yet, we can't model it. And we can't model the emergence of technologies that don't exist because if we knew enough to predict, the exact technology that would come forward and take over, we would really know enough to have the technology today, right? So all the technological advances are quite unknown, and you just have to, in many of the models, they just assume that productivity in the energy sector will just follow the same path as it historically has, which has not been much, or they just use current technologies or whatever. And again, I'm not blaming them for taking this approach because I don't know what I would do. But it does mean that these, if anything, are probably upper bounds on costs. Historically, with environmental regulations, it turns out that in general, the estimate of the cost of compliance with the regulation by industry is too high before the fact. Industry compliance is actually cheaper than expected more often than not. And one reason for that is just that when they're faced with a regulation, they start getting clever about ways to meet it and spend less money. But you can't know that that's going to happen in advance. And you can see that this, the range is huge. Right? If you think in terms of confidence intervals, they're way bigger than, they kind of dwarf the midpoint estimate. Now, of course, one of the standard things that you see in the political debate is that, well, we don't know for sure climate change is going to happen. It's uncertain. That's actually at the more rational end of, that side of things. And therefore, we shouldn't do anything. And so just because I always worry that talking about uncertainty will leave people with that implication, I want to disavow that right now. If you assume that the IPCC is right about that 90% chance, that's pretty much what lawyers tend to think of as proof beyond a reasonable doubt. Right? Proof beyond a reasonable, we could never convict anybody of anything if we required absolute certainties. Proof beyond a reasonable doubt means we're quite sure but not absolutely certain. We're really in that range for climate change. And then, of course, there's the argument that even if there's a chance that it's not real, the consequences of climate change are so severe that it would be foolish to ignore it anyway. So this is coming back and talking about some of the model limitations. Clouds are really surprisingly tricky. As I say surprisingly, I kind of hesitate over that because I actually have very little idea of the dynamics of what happens in clouds myself, so why should I be surprised that it's complicated? But it turns out that it is. And one of the easy ways to see the complications and the difficulties is by the disagreement over sensitivities. Nevertheless, despite all of this, you can see that the models are doing a pretty good job, not just at getting the general trend right, but also at getting some specific kinds of shifts right, like what happens with Pinatubo, for example. When you put in that there's a volcano, they all show the same cooling right afterwards. But, so there's, this is a comparison between temperature anomalies for natural forcing. So that's what the world would look like with just the natural forcing, is basically that gray thing holding constant. With anthropogenic forcing and with putting them both together, you get really pretty close to the shape of the actual distributions. And here's some more showing comparisons between models and observations. All that fuzzy stuff in the back, though, shows the uncertainties around the climate models and how different model runs are looking. And here's some more of the cost estimates of climate models. And again, showing you that this stuff is really hugely uncertain. Okay, so now, with all that as background, let me tell you, start to talk a little bit about at least the legal points. One question that I've been asked by climate scientists is whether this model stuff is going to be admissible in court. Can you get somebody to stand up in front of a jury and testify about their conclusions based on climate models? The test for introducing evidence in federal court is called the Daubert Test, after a case name. And it relies on several factors, which are, I've listed the key factors here. I'll come back to them, but you might wonder, why do we even have a test? Why not just let all the evidence go before the judge or jury, and then they just take it for whatever it's worth? Why have rules that keep stuff in or put it or leave it out of evidence? One of the reasons, and the one that you hear the most from lawyers, is concern about juries. We're not super confident of the ability of juries to separate good science from bad science in a trial setting. And there's no way of eliminating that entirely, but to reduce the sort of riskiness of that process, the idea is to keep the junk science out of the courtroom, right? So that you don't tempt the jury to go after some guy with a really, kind of far-fetched but theory that sounds kind of plausible if you don't know anything. So we have this test in large part maybe, to protect juries from being misled. There are some more subtle reasons, however. One of them relates to the way lawsuits are staged. Before you get to an actual trial in a civil lawsuit, there's a stage called summary judgment. At summary judgment, you have to basically put up or shut up. You have to put your cards on the table, show what your evidence is, and persuade the judge that you've got enough evidence to justify the trial. What these evidence rules allow you to do is to filter out the bad stuff at that stage too, so that the judge is limited to considering really only the reliable evidence in determining whether there's enough to go forward and go to all the time and trouble and expense of an actual trial. The summary judgment stage is based on paper, right? So it's much more economical in terms of its demands on the system and its cost for the parties and so forth. So we want to filter out bad cases there, cases that don't really have evidence behind them, and being able to just reject unreliable scientific evidence allows us to do that filtering. So I think these are relatively common sense. Now, some of these are aimed at things like typical forensic evidence, like the known or potential error rate. They're worried about things like voice prints and DNA testing and other kinds of things where the error is misidentifying a person or failing to identify the right person, and you just want to know how often that happens before you let the evidence in. And it turns out, in fact, that a lot of traditional kinds of evidence, like handwriting experts, you always see handwriting experts on TV shows. It turns out really, really weak evidence. They're really bad at being able to tell. I mean, if handwriting is very similar, they can tell you that, but it's very hard for them to actually tell anything about identifying specific handwriting when you actually go out and test it and statistically. So that's an important factor for identification evidence. It's harder to apply to the kind of models we're looking at now just because we'll only know the error rate if we wait a century. But it gives you the idea. Notice that peer review is very important. It says relevant here, but a lot of judges take it to be more than just a relevant factor. They take it to be like the key factor. So the courts are really relying on the peer review process to weed out bad evidence. Has it been tested? Right? So you find a lot of cases, say, dealing with chemicals where some guy comes into court and he's got some theory about how a chemical might cause some effect. And the theory is actually, sounds like, well, maybe it could be right. But in fact, there's no evidence. Nobody's tried to determine if it's true. There's no empirical evidence, no laboratory tests, no nothing. And obviously that should get a lot less weight than something that's, where you actually have some hard evidence behind it. General acceptance in the field, it's certainly possible. In fact, I think it's almost certain that there are things that 99.9% of physicists believe today that will turn out to be wrong. Nevertheless, if 99.9% of physicists think something, that's by far the best bet for the rest of us. It would be foolish to overlook something that the experts agree on. On the other hand, if something has not been accepted, if it's regarded as being kind of an outlier theory in the field, that suggests that it's kind of risky for us lay people to buy into it. So these are the factors. There is now a federal rule of evidence that was based on these cases, which I've reprinted here. So you notice, like a lot of legalese, it's got lots of, repetitive clauses. Knowledge, skill, experience, training, or education may testify in the form of an opinion if the testimony is based upon sufficient facts or data, it's a product of reliable principles and methods, and the witness has applied the principles and methods reliably. So reliability is really the keystone here to the admission of evidence. And that's going to apply not just to this modeling stuff, but, for example, to readings that, from nanodust, right? So you want to know how reliable are these things, is this nanodust, how much has it been tested, do we know what it does under different circumstances, et cetera. If it's reliable, if you used it correctly, because that's always an issue, then, and if it's helpful to the jury, right? There's a lot of interesting scientific evidence that's really not germane to the case and very peripheral, but if it's on an issue the jury needs help on, then you're going to get it in. The courts have not really had a chance to consider much the specific question of using climate models, right? This is new stuff. Climate change litigation itself is pretty new. So we're just beginning to develop some experience with climate models specifically. There is some, at least, indirect support from the Supreme Court's only decision relating to climate change, Massachusetts versus EPA. This was a case about EPA's authority to regulate greenhouse gases under the Clean Air Act. That's still a controversial issue today, but as a result of this case, EPA is moving toward imposing those regulations. A lot of people complain that this shouldn't be covered by the Clean Air Act, et cetera, but it actually, in this decision, the Supreme Court basically decided the legal issue of whether climate change is within the Clean Air Act. So people shouldn't be blaming EPA for this decision. One of the issues in the case was whether the people the plaintiffs in the case, which were the state of Massachusetts, state of California, and a bunch of other organizations and people, whether they were actually injured by climate change. Because one of the rules in the U.S. legal system is that you have to show a personal injury or direct injury in order to bring a lawsuit. You can't just read something in the paper and, go to court and say, it made my blood pressure go up when I heard about this. You've got to show that whatever the government is doing, for example, is actually going to harm you. And so in this Massachusetts case, one of the major issues was whether the plaintiffs could show that they were actually going to be harmed by climate change. The Supreme Court said yes, 5-4. In coming to that conclusion, the majority relied on affidavits and by climate scientists and on like a National Academy report. And those things in turn were based heavily on modeling, right? So that suggests that the court is sympathetic to climate science and willing to accept these results. But they weren't directly asked about the question of admissibility and evidence, right? So it's not direct precedent. But still, it gives you a little more sense of comfort, I think, that the court thought that this evidence was good enough to make use of itself in this case. Just as an aside, one of the forms of injury that the court was most impressed with was sea level rise and the prospect that the state of Massachusetts would lose coastal land because of sea level rise. Now, there's also been at least one trial court ruling directly on the admissibility of modeling effects. This was in a case that involved California's Pavley Act. The Pavley Act is California's law regulating greenhouse gases from motor vehicles. This was challenged in several different places, one of them in Vermont. And you wonder why California law is being challenged there. It's just one of the oddities of the legal system. But one of the issues in that case related to the severity of climate change, the effects it would have on the state of California, because California was arguing that the law is justified because of California's own stake in climate change. The court relied heavily in deciding the issue on the testimony of the director of the Goddard Institute, who was a well-known climate scientist, and he testified, at length about the evidence for climate change, the likely effects, and the possibility of tipping points. The court found that was clearly admissible evidence, that it was based on reliable scientific sources and methods, and that it should be introduced. And I think that's, I would say, clearly the right answer, because if you look at the efforts that are made to assure reliability of these climate models, they actually go well beyond just the traditional peer review process. There are all kinds of other input points for experts to criticize model runs. There are efforts, for example, to run all the models off the same data set just to see what happens and how they're different. Conferences trying to analyze differences in the models, or places where the models seem to be getting things wrong. It's a very self-critical process, a very self-conscious effort to validate and revise where necessary the climate models in a way that I think is kind of a model of how to do this kind of science. And so the court, I think, was quite right to find it admissible. There's also a little more detail in the case because one of the witnesses relied on some specific models, the Hadley model and the Canadian model, claiming that they were defects in these particular models. And the judge rejected that criticism and found that the witnesses from the defense were outside the scientific mainstream, and also emphasized that the models had been selected for use by the government, which is kind of a seal of approval on the models. So I think actually one thing that's questionable after this decision is whether testimony by climate deniers would be admissible in court. I mean, it seems to me, I think, in fact, a very powerful argument that this is exactly the kind of outlier, unreliable evidence the courts should not be allowing in, as opposed to these mainstream climate science results, which have been through this very rigorous process. One of the things that's notorious on the climate denial side, for example, is how very, very little of it has ever made its way into peer-reviewed journals, which is one of the key factors under Daubert. Now, one of the things that complicates all this is the trial judges actually have leeway in deciding what to let in and what not to let in. So in a way, although they're legal tests, they're kind of a little bit spongy, right? There's a big zone where the judge can decide yes or no. I mean, some things the judge is going to have to let in or get reversed on appeal. Other things, if the judge has to exclude or get reversed on appeal. But there's a middle range where the appeals courts are likely to say, hey, it was the judge's call. And there are a couple reasons for that. One is that the judge has a more intimate knowledge of the case, has probably actually seen witnesses that the appellate court hasn't seen. And also because you don't want to have, if you ordered a new trial for every little borderline judgment call that the trial court made, you'd never be able to end litigation. As a practical matter, in order to have trials that have some sticking power, you've got to give the judge who's running the trial a little bit of slack. Now, what that means is that it's really hard to say with 100% certainty, even harder than it is in many legal settings, whether in a specific case you can get specific climate evidence in, right? Because it's going to depend both on the specific evidence, but to some extent on the judge. But I do think that at least as to the kinds of main results and main modeling outcomes from climate science, that a judge who did not allow those in would be reversed on appeal. Now, although people tend to think of courts when they think about the legal process, in fact, a lot of the most important decisions are not made by courts, they're made by administrative agencies. But courts have the ability to review what administrative agencies do. And one particular important stage in the administrative process is the review of cost-benefit analysis by the Office of Management and Budget. So there's been a rule since the Reagan administration that new regulations, major new regulations, have to be accompanied by a cost-benefit analysis. And unless there's a legal exception, the regulation has to pass the cost-benefit analysis. So you see lots and lots of fights between OMB on the one hand and agencies like EPA over specific regulations. And it's at this point that I think that the question of models comes in. Again, first, the reliance by agencies on the climate models, and second, the use of the economic models in the cost-benefit analysis. Now, OMB has recently issued a rule. That shouldn't be EPA in that first line. It should be OMB in the first bullet point. Recently has issued conclusions about the social cost of carbon. That is, a monetary estimate of the harm done by 1 additional ton of carbon in the atmosphere. They did that using 3 of the economic models. But they also did a sensitivity analysis. Discount rates reflect how heavily we take into account events in the far future, right? So the higher the discount rate, the less we care about the future. And it turns out to be a very important, although very technical, determination. EPA used 2 different discount rates as part of their sensitivity analysis. They also included the 95th percentile estimate as a way of trying to get at some of the risks of climate change and climate uncertainty. And what they came up with was $20 a ton of CO2, which is ballpark $7 a ton of carbon. Actually, a little less than that, but that's controversial among economists and certainly with environmentalists. The point that I would make, there are a lot of specific criticisms you can make. One of the models I think is really pretty bad, the one that gave the most optimistic vision of climate change. None of the models take much account of the risk of catastrophic climate change because economists really haven't been able to figure out how to build that into the models. And the confidence intervals were based on a meta-study that had serious problems of its own, primarily because the guy who did the meta-study counted each of his previous model runs as a separate study. So it was like, 3/4 of what he was doing his meta-study of was his own work. Not a great job, but I think more fundamentally, it's just not clear that no matter how well they do it, that the numbers are going to mean a whole lot, just because there's so much uncertainty about the extent of climate change, the details of how and when it happens, how much we can adapt agriculture and other things to respond to climate change. Many of the models assume perfect adaptation. That is, that we will costlessly and instantaneously, for example, change our agricultural patterns and develop new varieties to deal with new patterns of temperature and rainfall. That seems like a sort of heroic assumption. So I'm not sure that in fact that's going to do you a lot of good. The meta-study shows the mean social cost of $50, but look at the range. A 10%, so the 90% confidence interval is up at 125%, and 95% is up at $245. And the confidence, the 95% confidence interval goes from -$9, carbon's good for us, but not very much, up to $245 of harm on the other side. At this point, it seems to me you might as well just, call it a guess. Now, of course, one of the problems is, well, if you're not going to come pick a number like that, what are you going to do? That's really hard, right? We've got pretty good ways of analyzing situations where we can attach probabilities to the outcomes. We've got sort of conventional statistics, we've got Bayesian statistics, we've got risk assessment, we've got all these things. We don't have very good ways of knowing exactly what to do when we can't do that, right? When we're too uncertain. We can't even really we're not even comfortable putting numbers on things. So there's some interesting work going on in trying to deal with that today by economists and others. Some of it, in the mode of economic theory, the RAND people are doing some interesting stuff with a kind of computerized scenario analysis that tries to develop and refine robust strategies. So the idea is find strategies that over the broadest range of possibilities will work well, will save you from disaster. And I think that's very promising. But we have a long way to go. Nevertheless, the fact that that it's convenient to have a number doesn't necessarily mean we should just pick a number just so we can use our familiar analytic tools. But that's something that I think regulators in particular are going to be struggling with as time goes on. Another thing that we can do is just try to improve our numbers. There are various possibilities of doing that. There are thoughts about what the actual distributions are likely to look at and how to sort of go between data points and things like that. And I guess with that, I will open it up to questions. Obviously, we've got a lot of interesting stuff that we're going to be confronted with in the next few decades.
Thank you, Dan. The connection between energy, which is the topic of these seminars in general, and climate change, they're inextricably linked. We've talked about that for years and years, and so this is very relevant and I think applies to a lot of things outside of climate change, so some of the fundamentals here. Forgot to introduce myself at the beginning, very rude to the audience. I'm Gary Baldwin with I for Energy, and we are now open for questions here and afterwards. Do I see a hand? Yes.
Yeah, Carl Brown, CIEE. Dan, you mentioned the 5-4 Supreme Court decision on the including the issue of whether it's an air quality issue. In that decision, did the minority report or the minority decision in any way challenge the evidentiary issues, or was that based on the nuances of law?
They did not challenge the evidentiary issues, although they didn't really endorse them either. So I guess that you would, at least reading the minority, the dissenting opinion, have the sense that climate science was a bit more uncertain than we actually think it is. But they did not rest their views on a rejection of climate change. And in fact, they really couldn't have done that because the Bush administration, by the time this case came to the Supreme Court, was admitting the reality of climate change. So the Bush administration was, although they were still saying there was a lot of uncertainty, but they basically had given, it's quite interesting, I think, the way that evolved over the 8 years. By the end of the time, they really were admitting climate change, saying it's serious, but just arguing that it required international negotiations rather than intervention by the courts.
You mentioned that you didn't have a way to deal with productivity increases, though given the 20th century you developed universities and labs and big science, very big way, a productivity increase is just built into the system, so not including it is just unrealistic. So what do you see in terms of legal possibilities for the different numbers for productive increases to be peer-reviewed and legally determined that these actually make sense and aren't just pulled out of the hat by an advocate for a particular position?
Right. Well, I think the overall issue of general productivity rise, although economists don't really entirely understand what drives productivity rise, it's clear that science and technology are a key factor. I think in terms of the overall economy, you can make plausible estimates based on history. We can't know if they're right, but they're kind of plausible. But one of the big questions is what happens specifically in the energy sector. Are we going to have, how much technological progress are we going to make in the energy sector? And that's trickier, right? Because now you're getting down to a much finer level. A lot of the early models assume, actually almost all the models assume, that providing incentives for new technology, that putting a cost on carbon won't produce technological improvements, right? So the assumption is that the energy sector will stay in lockstep with the overall rate of technological improvement. And that providing sector-specific incentives won't have any effect. Now, that can't, I shouldn't say that can't be right, of course. Anything could be, but at least that's quite contrary to most of what economists believe about the world. Economists generally believe that if you give people incentives, that will change their behavior. And that if you give people incentives to find lower cost, more efficient technologies that produce less carbon, that incentive will have an effect. But I think I don't think we're yet at a point where anybody can make a very confident quantitative estimate of what that's going to look like. But, it is something that economists have sort of taken note of and are beginning to try to work on.
It's one thing to accept that we have climate change, that's one thing. The other thing is cause and effect relation, which is implied in all of these cases, and I guess lawsuits and general public opinion and so on. Now, if uncertainty of all these predictions are so critical to policy making and outcome of cases, why there is no more stress by policymakers on quantifying uncertainties? from my end, I think you're too optimistic about trusting these models. I'm all my life doing modeling of simpler problem, combustion, and I can tell you with all assurance, we cannot predict a thing. So, and never mind, you know, a lot of these success stories are basically wishful thinking, driven by pressure of success by funding agencies, policymakers, and so on. It's not real.
Well, since I'm not a modeler, I guess I can't respond to that in detail. But at least it appears that there are some good indications that the models, even if not correct in detail, are getting at the important processes, both because you're getting the overall trend of 20th century emission increases, but also because you're getting a lot of the nuances of the increases, such as what happens with Pinatubo, or what World War II, which and the Depression do because of their effect on industry. So it looks like we're basically getting the right sort of shape. The other thing is that if you look at the model runs that leave out the CO2, you get nothing like the 20th century weather pattern. Right? I mean, you just don't get evidence. People talk, for example, about changes in the sun, and it turns out that probably those would be driving a cooling effect right now, and that when the sun goes back to its sort of average normal luminosity, that cooling effect will disappear, and we'll see a big jump in warming. So I'm nervous about models too, because. Particularly because these are very big, complicated models. It's very hard even for the people who do them to have a really good grasp of what's going on inside. But I do think, but they do, to the extent that you can test these things, they do seem to be validating the thrust of what the models are telling us. I should also say that we have a lot of evidence about climate change that doesn't come just from the models. It comes from things like ice cores and studying other kinds of weather information. So these models are important, especially in trying to figure out what to do about the future, but only part of the story. I think the quantifying uncertainty is really important. The fourth IPCC assessment makes some efforts, at least on the basis of the models, and their outcomes, to come up with sort of a probability distribution, actually two different probability distributions. One of them just treating all models equally, and the other one weighting them based on how well they do with 20th century predictions. And so we're beginning to get some quantification sense, but I'm not sure, especially given this question that you raised about what if they're all wrong, right? Then, and at that point, it seems to me we have to confront the fact that they could be equally well wrong in either direction. That is, if there's something basic that's being left out, or some basic problem with the way we're, say, modeling clouds, it could be that climate change is not going to be a problem, or it could be, in fact, that it's going to be twice as big a problem. And so it seems to me that that only sort of increases the risk factors that are posed by greenhouse gases, because we'd be in a much better situation if we just knew exactly what was going on. We would pay a lot of money to know exactly what's going on. I mean, that would be very valuable information. When I talk to people, I sort of ask them informally, what do you think the chances are that we'll be able to eliminate these uncertainties through model improvements and so forth? The answer seems to be, yeah, we should gradually get better. But it's not going to go away overnight. One of the problems is we don't have enough data, which I4E comes into. Our detailed climate records don't go back far enough. They don't include a lot of things we would like included about like what's happening with different gases in different places and so forth. We could do a lot better job with fine-tuning the models if we had better data to put into them. And so that's one where I think what's going on at CITRIS may be especially helpful. Thanks.
Great. Let's thank him again. Great talk.